somebody responded just immediately.
Several people.
Yeah.
Yeah, so that's what's nice about Discord is so when I'm on my computer doing stuff, if I'm grading or making assignments, I'll usually be logged into the server. And if somebody posts something on there, ask a question, I'll see it right away. I may not respond to it right away, but if it's something time critical, there's a good chance that I would, just fire off a quick response right there. I don't have to open up email and all that kind of stuff, and it's just nice for quick throughput. All right, so let's start with discrete structures. We've done the administrative stuff and so on. So our first topic is set theory, right? And as I said, sets are at some level of a very simple concept. So we can think of a set is a collection of things and I use the word things deliberately because it could be a set of integers, it could be a set of animals, it could be a set of teachers, but it could be a set of anything. It could be a set of animals and integers, right? There's very little restriction on what can be in a set. It's really just a collection of things. One restriction is it's an unordered collection of things. So if we have a set of markers, a black marker and a blue marker, that's our set. It contains two things. There is no notion of what's the first element in the set. There's no ordering to it. This set would be exactly the same thing as that set. Okay, it's simply a collection of things. And if we pick anything in the universe, we can say, does this belong to the set or does it not belong to the set? That's the whole definition of a set, what things belong to it. Not what's the first thing in the set, what's the last thing in the set, because there's no ordering to it. Okay, now when we write sets on paper, or when I show you a set, yeah, this is the first, this is the second, right? Obviously, if you happen to go from left to right, or from top to bottom, or bottom to top. But there's no inherent ordering to the things in the set, so it's an unordered collection of things. And so we use letters to represent sets. So let's say, suppose S is a set. And I haven't said what it's a set of, but it's some collection of things. We can talk about, is some object in the universe a member of this set? So we have a lot of shorthand when we do math. We can write this hunchback E, this epsilon, X, epsilon S. This means X is a member of the set S. And if we write that epsilon with a line through it, that means X is not a member of the set S. So just some shorthand there for working with sets. So examples. Let S be the set of integers. So integers are just whole numbers. It's mostly what we work with in this course. Sometimes we'll work with real numbers, but mostly we're going to work with integers or small sets of integers. So S might be the set of all integers. So what are some of the things that would be in S? 5, negative 17, 0, but 3.14 is not a member of S. And a triangle is not a member of S. And a three-legged zebra is not a member of S. These are valid objects, but they're not elements of this set. Well, we know what integers are because we've studied that elsewhere, but we'd like to have some way of representing what this set S is without necessarily using the word integer. So here's one way to do this. We usually represent sets with things inside curly brackets separated by commas. So we could list the number 0 and the number 5 and the number -17 and -16 and 1 and 2. We could try to list all the elements of this set, but it doesn't work well for integers because there's an infinite number of integers. And we could say ... but what does that mean? What comes after 1 and 2, right? So here's one way we could do this. And we would argue that most reasonable people who have worked with integers and discrete structures and sets would probably understand what this means. Because this clearly looks like we're dealing with integers, could be positive, negative, or 0, and the ... on each end means continue this pattern. Well, the pattern's pretty clear, right? Should go from 4 to 5, 6, 7, -3, -4, -5. This is all integers. But this can be tricky sometimes, right? Suppose I do this. Well, we might say this is all the odd numbers, or it could be just all the odd prime numbers, the numbers that aren't divisible by anything other than themselves and 1. We don't know if 9 belongs to this set. So we want to be a little careful using this ... notation. Right, unless it's really clear, and we could write something in words like S equals a set of all integers, if we weren't sure about the ... notation. But some of these sets, we have particular symbols we use to represent them. So we have a special symbol for the set of integers. It's this funny Z. It's got a double line on the slant. So this is a set of all integers. And this funny R with a double line, this is the set of all reals. So the numbers we usually deal with in, say, a calculus class. And a funny Q, this is the set of all rational numbers. Do you remember what, does anybody know what a rational number is? I know you do. It's basically a fraction. It's a number that can be written as integer over integer. So 1/2, 2/3, 95, 713ths. These are all rational numbers. So there are numbers of the form m over n, where m is contained in the set of integers and n is contained in the set of integers, and we usually have to specify n is not 0 because we're not allowed to divide by 0 in most courses. So they're fractions. And there are real numbers that cannot be written as integer over integer. This was a highly disturbing realization to the Greeks. You've heard of Pythagorean theorem? Did you know he was kind of a cult leader? So he was the head of a group of people who worshipped numbers, and they attributed magical spiritual qualities to numbers. And they believed that if you understood these numbers, these integers, sufficiently well, you could understand everything, right? They saw it as sort of a divine pathway to enlightenment. And they had a cult, and it was secretive, and they had meetings and things like that. I don't know if they had a secret handshake. I like to imagine they did. And, you know, integers, so here's 4 units, and here's 3 units, and hey, this diagonal turns out to be exactly 5 units. How beautiful is that, right? 3 things and 4 things, and you get 5 things. So a Pythagorean triple, 5, 12, 13. They studied these things a lot. Well, there was one thing that kind of bummed them out, which is if you take sort of the simplest triangle, which is just 1 on each side, and you try to measure the length of this diagonal, they could not find a fraction of 2 integers that gave you exactly that length. They wanted to write this as integer over integer, and they were having trouble doing that. And eventually, a member of this group came up with a proof that you could not do this. There was no fraction of integers that gave you this exact length. Now, if you know the Pythagorean formula, we know that this has a length square root of 2, square root of 1 squared plus 1 squared. They didn't know this at the time. They didn't have square roots. But the length of this is this number, which is approximately 1.414. But it's not 141 over 100. It's not 1,414 over 1,000. Those are approximate. But no matter how carefully you choose these two integers, that fraction is never equal to square root of 2. That's a number which is, strictly speaking, not a member of this set of rationals. It's a real number. It's not a member of this set. And man, did that rain on their parade. Because this is like a really simple object, just a triangle, one on each side, and this length can't be represented by a fraction of integers. There's something more out there than just whole numbers. And that really sort of like killed the whole idea. So what did they do? Well, they didn't tell anybody about this. It was a big secret. And there was a member of the organization who actually told some people outside about this. He was in his 80s, I think. And they took him out on a boat and they pushed him off. And he actually swam back to shore and survived. But I mean, they tried to off this guy for like telling people about the square root of 2 and the fact that it's not a rational number. Because it really, really is a weird concept, right? Especially if you think that everything can be a fraction, and to find out that these things aren't. We'll prove eventually in this class that square root of 2 is not expressible as a fraction. It's actually a pretty simple proof once you've seen how to do it. But I don't know how somebody came up with it the first time. So there's fractions and there's all reals, and this is a strictly bigger set than this. There's another set, and we won't deal with this. This is the set of all complex numbers. Well, what's a complex number? Same thing that happened to Pythagoras and his followers when they were trying to do this. Really simple algebra question. Okay, x squared minus 4 equals 0. Is there a solution to this? What's the possible value for x that makes this true? Yeah, x equals 2. That's a solution. Is there another solution? Yeah, x equals negative 2. That's another solution. All right, an even simpler looking equation, x squared plus 1 equals 0. There's no solution in real numbers. And it's the same thing as trying to find the length of this. It's like, it's a pretty simple equation. There should be a solution, but any real number you pick to plug in, this is going to be at least 0. When you add 1, it's going to be at least 1. Can't be equal to 0. So what did we do? We came up with new numbers. They're called imaginary numbers because they're not real, right? And we would call that number I, or if we're an engineer, we call it J. And it's just the square root of negative 1. So if x is equal to this mysterious thing, when we square it, we get negative 1. When we add 1, we get 0. So C is the set of all numbers, real numbers, but also these weird imaginary numbers whose square could be negative. And the point of this discussion, we're really only going to work with integers, occasionally rationals, not really reals or complexes, so you're not responsible for this. But the point of this discussion is that these things don't just develop at random. Hey, let's come up with a new subject we can torture students with. Let's make an imaginary number, right? They come up for a reason, because we're trying to study some system like triangles or algebraic equations, and we run up against a wall and we say, hey, you know, the understanding of numbers that we have right now is insufficient. There's got to be some bigger set of numbers out there, right? This is how mathematics and other things advance. Incidentally, you don't have to go beyond C. If you write algebraic equations and you allow everything to be complex, there's no equation you can write that you can't find a solution in this set. That's as big as you have to get. It's what we call algebraically closed. And there's a bunch of proofs of that from all sorts of different branches of mathematics, and it's some beautiful results. But we'll talk about that some other day. All right, so we have particular sets with particular symbols that we use. Mostly, we're going to deal with Z, which is a set of integers. Sometimes we'll deal with this set called N, which are the natural numbers. And natural numbers are the ones that we find in nature. We don't find half a cow in nature, right? We don't usually see square root of 2 trees out there, right? And we don't see negative trees or negative animals. So, so natural numbers are generally the positive integers, and sometimes they include 0, sometimes they don't. It depends who you're talking to. So if I'm talking about natural numbers in this class, I'll specify whether we're including 0 or not. And I'll usually just say positive integers and 0 or something like that. But they're sort of the counting numbers. And negatives are another weird concept that even before the Greeks, right, the idea of a negative something was weird, right? What does it mean to have a negative apple? And how is it that when you take a negative apple and you put it with a positive apple, you get no apple? I mean, that's like bizarre, right? It's an abstraction, it's a concept that took some getting used to, just like imaginary numbers. All right, so other ways that we can define sets. Let's define a set D. So we can write something like this. So what does this mean? D is the set of, so the curly brackets mean the set of X, where X is an integer. That's what the X contained in Z means. Such that, that's what this colon means. And sometimes we'll see it with a vertical bar instead of a colon. Such that this is true. So this line on top, we can translate that as follows. D is the set of all integers X such that X is divisible by 2. Which we might write as that. But this such as notation is really powerful, and we'll use it a lot. And if I don't specify the set of X contained in Z, this might be ambiguous. So I could define P equals the set of all X such that X is bigger than 5. Well, what are the elements of P? We don't know. Does it contain 6? Well, yeah, probably if X is allowed to be an integer. Does it contain 5.1? Well, only if X is allowed to be a real number, or maybe a rational number, right? So we need to say something like, you know, the set of all X contained in the integers, or contained in the reals, or something like that. And we'll look at other ways of specifying sets as we go forward. Good so far? So a lot of this is probably review, a lot of it is probably obvious, but like I say, we'll start building on this and we'll get to some more interesting things pretty soon, but more definitions. So we have what's called a singleton set. A singleton set contains just one thing. So the set containing the letter A, that's an example of a singleton. So is the set containing just a 0, or the set containing a smiley face, or any set containing just a single object. All right, here's a set, the set of all x contained in the integers such that x squared is equal to -1. Are there any members in this set? Is there any integer whose square is -1? No. Any integer, the square is going to be at least 0 or 1 or 4 or something bigger. So we could write this as a set with nothing inside it. And we have a name for this. This is called the empty set. And we have a symbol for it, which is a 0 with a slash. Now that is a set. It's a collection of things. It just happens to have no things in it. Right? It's like an empty house. It's still a house even though it's empty. So this is the empty set. The empty set is really critical to a lot of stuff. In fact, we can define the integers using the empty set. All right, other ways we can work with sets. We can use what's called interval notation. And interval notation, you've probably seen this in math courses. So if I write a comma b inside square brackets, this is a shorthand for the set of all x such that x is bigger than or equal to a and x is less than or equal to b. Now I didn't specify what x is. Is it an integer? Is it a real? It doesn't really matter as long as we understand what that domain is. I could use this for real numbers. I could use it for integers. I could use it for primes. Right? Anything where this notion of x is bigger than or equal to a, less than or equal to b makes sense. And this is also called a closed interval. We can also write this in parentheses, and this is the set of all x such that x is strictly greater than a and x is strictly less than b. And this is called an open interval. And it's not a coordinate pair. It's not like xy coordinates. This is a very specific notation. And you got to know from context whether this is the point a comma b on a plane or this is an open interval of numbers between a and b. So for example, bracket 3 comma 5, if we're working over the integers, this would be the set containing 3, 4, and 5. The open interval 3, 5, what would be the members of that set? Anything else? Right, that's just a singleton set containing 4. Pretty simple concept, right? You can build up calculus from this concept. You can use this and develop something called point set topology, which is basically abstract calculus. And if you apply abstract topology to the real numbers, you get calculus, limits and continuity and all that stuff that we do in 151. So it's a pretty simple concept, but it's capturing something really powerful. And here's an example. I'm kind of going math geek on you today. That won't always happen. But let's look at the real numbers. And let's look at the interval 3 comma 5. It's a collection of real numbers, bigger than or equal to 3, less than or equal to 5. What's the smallest real number in this set? 3, right? It's got an infinite number of elements, 3, 4, 4.26, 5, 7, 3, and so on. But 3 is the smallest element. What's the smallest element in this set?
Infinitely close to 3.
Infinitely close to 3, not a number, but right concept. There is no smallest element in this set. That's pretty heavy. This set has a smallest element, this does not. That's where calculus comes from in some sense. Okay, so you can go off on this stuff and you can lose yourself for a decade just abstracting further and further and further. There's a lot of power kicking around in these simple concepts. We won't go there, okay? We'll point set topology if you're interested, or if you bump into it down the road. All right, so here's a weird set I'm going to create for you. Is that a valid set? Is it a collection of things? I mean, Z is a thing. It's a set of integers. R is a thing. It's a set of reals. Here's a collection, an unordered collection of two things. That should be a set. Nothing wrong with that. So the elements of sets could happen to be other sets, or zoo animals, or whatever. Nothing wrong with this. But we'll come back to this probably on Friday in ways that will terrify us. All right, equality of sets. So here's two sets, 3, 5 and 5, 3. Are these the same set? Absolutely, because the ordering does not matter. There is no order, right? I've written 3 first because I'm on a piece of paper in 3-dimensional space. I got to lay things out side by side. But there's nothing inherent about 3 that makes it the first element. This contains 3 and 5. This contains 3 and 5. They're exactly the same set. So let's make a definition. A equals B means for all x, all things in the universe that we might call x is a variable, x is contained in A if and only if x is also contained in B. So saying A equals B means that for any object that we pick, that object belongs to A if and only if it also belongs to B. And the only if means if it belongs to B, it belongs to A. So things are either a member of both sets or not a member of both sets. And that's a pretty intuitive but long-winded notion of what equality should mean. It means the stuff that's in here is exactly the same as the stuff that's in there. And we have some shorthand for this, and we'll play with this a lot more in a few weeks. But for all x, we can write with this upside down A followed by the letter x. This is something called the universal quantifier, and it's just a shorthand for the statement for all x. And we can say x is contained in A, and if and only if we use so often, we have a shorthand for that, it's IFF. If and only if x is contained in B. So this is a fancier looking way of saying what we mean by A equals B. For all x, x is in A if and only if x is in B. What is this thing that I've just written? 3, 5, 5, 3, 3.
A set that contains 2 5s and 3 3s?
Yeah, it's a set that contains 2 5s and 3 3s. That's not going to be legal for us. Okay, we never want to write something like this, unless we put a frowny face next to it or something. This is not a valid notion of a set because a set is a collection of things. It cannot contain 2 of the same thing, right? A set is defined by the things that it contains. It contains a 3, it contains a 5, that determines the set. This is basically saying it contains a 3 and it contains a 5, oh yeah, and it contains a 5 and it contains a 3. Well, we've already said that, right? So the only way that we could represent this set would be like this, or like this, or a set builder notation or a definition or something like that. But we can never list a set where we list elements more than once, okay? That's going to be considered an illegal representation. All right, we got 4 minutes. I'm going to start on subsets, because then we can start doing some problems on Wednesday. So if A and B are sets here, and I should write on the top, let A and B be sets, but I'll just say it instead. Let A and B be sets. This notation, A, and then this sideways, like an elongated C with a line underneath it, this means A is a subset of B. Which means for all elements of the set A, that element is also a member of set B. So 1, 3, 5 is a subset of 1, 2, 4, 5, 10. How do we know that? If I put the 3 in. How do we know that? Because for everything in this set here on the left, that's an element of the set on the right. 1 is contained in here, 3 is contained in here, 5 is contained in here. Okay, it's just a definition of a relationship between two sets. A is a subset of B if everything in A is also in B. So this is like the original set A with possibly some extra stuff added in. Is this a true statement? Is 2, 4, 5 a subset of 2, 4, 5? Yeah? Feels a little weird, but every element here is an element of that. This is absolutely true. And there's nothing magic about 2, 4, 5. I could pick any set S, and it's always going to be a subset of itself. How about the empty set? Is the empty set a subset of the set 2, 4, 5?
Yes,
Why?
because it can, a set containing nothing can be inside of a set that contains something.
Yeah, I mean it takes some wrinkling of the brow to sort of come to terms with this, but if we think about our definition to be a subset, we require that every element here is also an element here. Well, if there are no elements here, so our condition is kind of satisfied in the vacuous sense. Now that may feel weird, it may feel like cheating, that's okay. Okay, hold on to that, because when we come to propositional calculus, we'll deal with if false, then I can fly kind of statements, and we'll address this more formally. But for now, let's just live with the fact the empty set is a subset of every set, right? So for any set S, S is a subset of itself, and the empty set is a subset of S. Simply because there's no elements in here that aren't contained in S, because there's no elements in here at all. So we always know these two things, but these things aren't really interesting to us. It's more interesting when we have something like this where the two sets are different. So this will take us to the idea of a proper subset. So we'll start with that on Wednesday, and then we'll go ahead and we'll do some questions related to this and just make sure we're on the same page. Then we're going to talk about sets of subsets, something called a power set. And then we'll start looking at ways that we can put sets together to make new sets. So unions, intersections, complements, and things like that. And this will be our first of many forays into something that will end up looking exactly like what we did in 250 with Boolean algebra. All the set operations we do are going to have analogs to Boolean operations we've done in Engineering 250. And that'll be a theme that'll come up again and again. All right, cool. I will see you next time then.